Welcome back. We're going to continue our conversation of algebraic properties in the dot product. Let's do a quick review of what we did last time. We started with vectors in R3, and we really showed three algebraic properties. The first one was the connection between the two norm of vectors in R3 and the dot product, and that said that the square of the two norm was equal to the vector dotted with itself. We also showed that the dot product was symmetric or commutative. If you're normal, you can call it commutative. If you're abinormal, you might call it symmetric. X dot y was equal to y dot x. We could switch the order with no cost. And then we are now working on the second part of bilinearity in this video. The first part of bilinearity we call linearity in the left argument, and we showed that when you have the dot product and vector addition, we can distribute the dot product over vector addition. Why I want to say linearity in the left argument, when you look at the vector addition, I guess you have to be a little careful here. This is what we call the left argument, meaning to say it's the thing on the left-hand side of the dot product. This right here we call the right argument. When you have addition in the left argument and then you pass the dot product through that addition, we're saying that that this has to do with left argument distributivity or linearity. One of the major questions about why we call it linearity, this goes back to a major theme in linear algebra. It comes up over and over and over again because this happens to be a very, very powerful operation in linear algebra. Lines are one of the only thing where you can pass multiplication or the operation through addition. If you look at squares, it doesn't work this way, right? I can't pass a square through addition. This goes back to a very, very classic mistake that young algebra students make. If I look at the... Oh, sorry, I'm trying to grab a pen here. So this is just a quick statement here about linearity. If I took x plus 3 squared, the square is a nonlinear function, which means I can't pass that operation through the addition. But when you have a line, let's say that you have the line y equals 2x. And then I actually took this line and evaluated at x plus 3. Do you see how the operation 2 actually gets passed to both arguments? This operation does not get passed to both arguments. This is nonlinear. In lines, when you have multiplication, lines through the origin in particular, the operation of addition actually passes through the operation of multiplication. This is a fundamental property of linearity. And that's what's going on here. You have this multiplication operation and an addition operation, and it just so happens that this operation is linear because they pass through each other. Do you see it? Distributing through. Okay, if linearity in the left argument has to do with taking vector addition in the left argument and then passing the dot product over that addition, could you guess what linearity in the right argument does? Ding, 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 ding. You got it. We would take the vector addition in the right argument, and then we pass through the multiplication. I like to call this making it rain, right? Making it rain means passing out dollar bills, right? So I make the multiplication rain over addition. Do you see it? I'm distributing. I'm literally giving out a multiplication to each term or summand in the addition. Okay, so linearity in the right argument says that I can pass through. Let's go ahead and prove this. And by prove, I mean let's actually show that this happens. So when we take x dot y plus z, I don't know, maybe we're feeling a little bit adventurous and we can skip a step. I actually don't recommend this for your first pass through, but some students say, hey, Jeff, we're a lot smarter and cooler than you are. And I say, yeah, that's actually really true, isn't it? And we can skip those steps without stress. So here we have an x2, here's x3, here's y2 and y3, and here's z2 and z3. So when we take this product, we take the product of the first two. Oh my God. So now we've got y1 times y2 plus y3, and then we've got z1 times z2 plus z3. And of course, all of these products exist in R1, in the space of real numbers, which means that we can distribute this multiplication over those additions. So now we've got x1 times x2. I'm feeling a little adventurous today, which means I'm not actually going to write the symbol. For any mathematician viewer, you're going to say, finally, what the heck's wrong with this guy? Why does he write it? I write it because I want to train my students to get used to trying to figure out what operation is being used. Here, you can tell this is an immediate scalar multiplication because the left is a scalar, the right is a scalar. You can tell this is an inner product because the left is a vector, the right is a vector. And when we specifically write them, it forces the reader to figure out what the heck is going on. Okay, so here we go. We've just distributed. Let's collect like terms. Here we've got y1, y2, and we've got z1, z2, and we're going to write those together. And now those take care of the first terms. And then let's look at the next term. So now we've got x1, x3, y1, y3, z1, z3. So that takes care of those three. And then each of those is an inner product. And in particular, this is x1, y1, z1 dotted with x2, y2, z2. This is the component definition. And then we add that to x1, y1, z1 dotted with x3, y3, z3. And this is now x dot y plus x dot z, which means we've just confirmed linearity in the right argument. I can pass dot products through vector addition. There's my second piece. And that works in both arguments. The reason this is the right argument is because the vector addition is happening to the right of the dot product. All right, let's keep going with our algebraic properties. The next one we're going to work with is something called homogeneity of the dot product. And this has to do with the connection between dot products and scalar multiplication. If I take, let's suppose that I took a times x, so this is a scalar vector multiplication, and then I dotted that with y. A times x would be ax1, ay1, az1. So because scalar vector multiplication, I just bring the scalar into each component. And then I go ahead and look at this as x2, y2, z2. When I multiply all this out, this is ax1 times x2 plus ay1 times y2 plus az1 times z2. But this is all multiplication in scalars, which means that all of this is associative, which means I could write this as a times x1, x2 plus a times y1, y2 plus a times z1, Z2. And what's really interesting about that is I could factor out the A because this is scalar multiplication. Of course, this should say Z2. I'm sorry about that. So here, that's Z2. And I have Z2 there. And then this is now A times X dot Y. Notice the output of X dot Y is a scalar, so this is a scalar multiplication because we're assuming this happens first. But I also wanted to show you that we could do the same thing up here when I have A outside. Because each of these multiplications happens in the real numbers, these are all commutative, which means I could bring the A in between and then reassociate. So this could be A times X2, Y1, A times Y2, Z1, A times Z2. And the reason that that's important is now this is X1, Y1, Z1, dotted with AX2, AY2, AZ2, which is just X times AY, which means it doesn't matter where the scalar is at the beginning. It could be in the front of X, so in the left argument, it could be in the right argument, or it could be outside of both arguments. Homogeneity means the same no matter where it happens, and that's what's happening here. The scalar can be pulled through in any sense. So the fast way to say this is AX dot Y equals X dot AY equals A times X dot Y. Doesn't matter where the scalar is. If anybody has a way to get well quickly, I pray that you would teach it to me. Okay. Let's look at our final algebraic property of dot products, which is the dot product with 0. And the way to think about this is if I take X dotted with the 0 vector, which means I go X1, Y1, Z1. Could you guess what the 0 vector is? Yeah, it's the vector with 0 components. So this would be X1 dot 0. Times 0. That's a scalar multiplication. Y1 times 0, Z1 times 0. And of course, all of those become 0. But since those are commutative, this goes into symmetry, right? Anytime you take the 0 vector, so anytime you dot a vector with a 0 vector, you always get 0 out. And notice, this is the 0 vector, and you can tell because there's a vector hat. This is the 0 scalar because there's no vector hat, and because the output of a dot product is a scalar. That ends the discussion of algebraic properties of the dot product. We're going to use some of these algebraic properties of the dot product, which literally came directly from the component definition, to now discuss the famous cosine formula for the dot product, which is really the geometric interpretation of the dot product. I'll see you in the next video.